As we bring up Clint Rubin for our next talk, I just want to say a word about his chair, Yishan Chin. Yishan is a SUNY Distinguished Professor himself, chair of the Department of Biomedical Engineering, director of the Orthopedic Bioengineering Research Laboratory, and co-director of the Institute for Engineering-Driven Medicine. His research explores the physical mechanisms that control tissue growth, healing, and regeneration with a particular interest in bones. He seeks to understand how those mechanisms treat and prevent disease and injury in bone mass tissue engineering. And he has many awards, but what makes him a really special part of the university is it seems like as he's become chair, he's become even more prolific as a researcher. It can be really hard to be a chair and continue to do the things that made you a great faculty member, but he has just really figured this out. He does this by being a great collaborator with others, and you can see this aspect of him in how he leads a department that is across 2 colleges. Now, these ideas are great in theory sometimes, but can be really hard in practice. But when you have a chair like Yishan, you're able to bring both great sides of what you get in engineering and what you get in medicine. And the way he is able to bring that together, support the faculty, staff, and students in that department, and again, continue to be sort of a model for what it means to be a scholar, but also a leader at the university. So, Yishan.
Thank you, Carl. I'm humbled, and because I have a great model to follow, Clint Rubin. All right, so it's a great honor to introduce Dr. Clint Rubin. I think he has a long history, and his academic history in Stony Brook starting in 1987. And he got the bachelor degree from biology in Harvard University, and then doing the postdoc in the anatomy in Tufts University and also Harvard General Mass Hospital. And then he joined us in 1987 to orthopedics department, and soon after, and you can see his background is biology, a little bit medicine, and then soon, and he is very interested in engineering. So then he actually helped the university build the linkage between school medicine and engineering and all other departments in the campus all together. So he became the founding chair for biomedical engineering department. First, we built the graduate program, and then undergraduate program, and then established department in 2000. So he served as a founding chair for 18 years. And then we grow from 4 founding faculty member to now 25. So it's a big jump, and try to link all the resources in the university all together. And today, I said our BME department truly become public university #1 in New York State, and no others. We even beat NYU. And then we nationwide, we have 24 in public university. So Clint built a great foundation for us. And so Clint is active, enthusiastic research in our society, and he tried to bring the engineering, biology, medicine all together. And his own research is more like bone adaptation, tissue engineering, and a crosstalk between bone and other tissues. So, for example, like a fat and bone and the neuron system, even cancer. So his method try to do is that try to connect the clinical problems, significance, with engineering method, which is in the future, if we can use non-drug treatment to those severe disease, osteoporosis, osteoarthritis, even bone cancer, how cool is that? And his research is really well recognized. And he published more than 300 journal papers. And then his citation is truly amazing. His Google citation is more than 44,000. 44,000. And then the H-index more than 100. So those achievements allow him to, in our field, it's a very distinguished scholar and with great reputation. And also he's an entrepreneur. And he actually very pay attention to the translation. And you can hear he is an inventor for 26 issued US patents, and also 38 foreign patents issued. So then he successfully found 4 startup companies, and then still several companies still going very well. And he also is a major player in Campus for Translational Research. He's a director for Center for Biotechnology, which is a New York State-funded advanced center and focus on the innovation, research, translation, and from bench to bedside. He's actively play a very important role to the campus-wide, forming several companies, leading the industry liaison, and leading to the efforts to rising federal grants and industry support. And these projects are clearly translational and impact to Long Island economy and New York advancement. And he is also an outstanding mentor. He trained more than 47 PhDs and the doctoral students, and also postdocs. Many of them still very active in the field, even include the National Academy member in engineering. I personally was very fortunate to be one of Clint's mentee. And then at that time, I think, maybe 20, almost 30 years ago, and he is very active, and I still remember we worked together day and night, do some experiments. And you can see the picture, that's the turkey. And then many people ask me, why Clint sit aside with a chicken? I said, no, this is turkey. And actually, it's my turkey. So when National Geography asked him, oh, we're going to have an interview, and Clint asked me, oh, can I borrow your turkey? I said, yes, but my turkey just shipped, and it looks like a chicken. So we do treat the animal very well, and usually those turkey can be grown very beautifully. Indeed, he's an outstanding advisor. So at that time, I remember, because at that time, we are writing papers, everything has to be very detailed. And my English at that time is quite poor, and he corrected every words and for me. And we don't have a ChatGPT at that time, certainly. So among the numerous achievements, Clint is also recipient for the several important awards. For example, 4 Albright Awards, and then Liner Kappa Delta Award for American Academy of Orthopedic Surgeons. And he also a fellow for several important societies, for example, MB and the AAAS, and the National Academy of Inventors, Biomedical Engineering Society, and also the American Society for Bone and Mineral Research. And without further ado, and let's welcome Colonel Rubin.
Thanks, Jen. Sound a bit like an obituary. So thank you to the provost for inviting me, and Monica for inviting me to participate in this and sort of to see sort of the spectra, pun intended, of the work that's done at the university. We've just heard about neutrino oscillations, and we're going to move forward, fast forward about 10 billion years to talk about oscillating or vibrating sheep. So there is kind of a connection there. It was a lovely talk. Thank you for that. I sort of got lost with the 10 trillion neutrinos going through my hand every second. It's a little intimidating, but what I'm going to do specifically is to talk about what we do in our lab group to develop ways of treating or slowing complications of aging without using drugs. And part of the punchline is this sort of picture of vibration, which is sort of where this all hunts down. If you can't read this, it says, try this. I just bought 100 shares. I'm sort of the poster child for conflict of interest at the university. It's something I'm very proud of. These are, Ishan just mentioned, some of the companies that I founded that range from companies that have gone public to here at the bottom is a company we've just started with colleagues in BME, including a graduate student. So it's the idea of sort of catalyzing innovation through the great research that's done at the university. I'm a huge fan of, and everyone should consider it. So both the conflict and the opportunity of seeing your science translate into technology. So what I'm going to do is really focus mostly on the musculoskeletal system in dealing with frailty and falls, sarcopenia, muscle wasting as a function of age, or osteopenia, osteoporosis, bone wasting as a function of age. And these are the sort of things that when you fall and fracture a bone, particularly if you're over the age of 70, which I now am, it really sort of starts a clock, which is really a scary clock for frailty and leaving the world. So falling and fractures, not a good thing. There's also with age, our immune system starts to get quite depressed. Our T cells, they reduce in numbers and they get exhausted much more quickly. So we're more susceptible to things like cancer as we age. And then finally, cognitive decline, dementia. We tend to become senior administrators at universities, this sort of thing. But there is one sort of unifying principle that sort of ties all these together, and that is exercise, right? So this is just last night, I just started going through PubMed, putting in exercise and cancer, exercise and Alzheimer's, exercise and breast cancer, exercise and all these sorts of things, and it just basically comes out and shines as something to slow these conditions down, right? So just, you try it yourself. I think one of the ones that I found most interesting, which I don't really know what it means, but I put in the idea of exercise and slowing cognitive decline, and it came up with acoustic streaming in C. elegans forced to swim as a model for looking at decay in cognition. So science is just a wonderful primordial soup, no doubt about it. But for those of you who are not particularly interested in publishing in Cell or Nature or Science, you can use one of our favorite scientific journals. That's the New York Times. You can also do a quick search on that, on exercise and aging. And they're quite nudgy about it, right? They say, go out, lift weights. You know, heavier weights are better. Or go out and play tennis against Venus Williams. It's really good for you. Do something like, run 10 miles a day. Why not? And yes, there's no doubt, particularly as it's published in the New York Times, it must be true. But this came out a couple of days ago. It looks like November 8th. Exercising is the worst, right? People just don't like to do it. So even if I told you it was just nirvana in terms of your health, the question is, how do we get engaged in it? How do we keep doing it? And particularly for we distinguished professors who were all over the age of 70, what can we do instead? And so this is sort of where I'm going to start the focus on these Yishen in his very kind introduction, talking about how mechanical signals or non-drug signals influence form and function. It's kind of easy to look at it in terms of the musculoskeletal system. But here we got Yannick Noah. The tennis ball is somewhere up in the ceiling, who knows where. But the point of this is that if you look at professional tennis players' arms, they have about 35% more bone in their playing arm than the arm that simply throws the ball into the air. So what you're seeing there is sort of focal and local adaptation to mechanical challenges. So bone and muscle goes both ways, right? That one of the problems of going up into space is the rapid decline in the musculoskeletal system. And just comparing to sort of Yannick Noah and sort of the challenge in the humerus or in the arm, you've got astronauts not losing 2% per decade or 2% per year, but 2% of their bone per month. So you could think of everyone so eager and anxious to get to Mars in a 9-month trip to Mars, you're going to be there with 50% less bone. But thanks to all those neutrinos passing through your head, you're going to end up with 15% less brain. So it's probably not going to be a priority. But do keep that in mind for you couch potatoes, that there is that decline of the musculoskeletal system. Now, just to use your imagination just for a second, these are vertebrae, not from the same person, but looking by 20-year jumps, 20 years, 40 years, 60 years, and 80 years from segments of your spine. And what you see in these struts are things called trabeculae. That's what gives you your bone structure. And anyone who's interested in aging and musculoskeletal decline will look at something like this 80-year-old spine and say there's a lot less bone. And that's why the structure is not there, and that's why we can get Dowager's hump, that's why we lose height as we age, et cetera, et cetera. But just for a moment, look at it, and those voids are basically indicative of more and more fat. So yes, we're losing bone, and yes, we're gaining fat. Okay, and there's some decision that cells are making because they come from a common precursor called a mesenchymal stem cell that usually forms bone, but under some circumstances decides to form fat. The same is true in sarcopenia, or muscle wasting, as a function of age. And in these scans, you see a male age 25 and a male age 63 of the same body mass index. So this is not a party trick or a cocktail trick. This is same BMI, but in this scan, the white is fat. And so as we age, we're all told that our muscles get weaker and weaker through sarcopenia. It's wasting away. It's being displaced by fat. It turns out that it's pretty selective, that the muscle fiber types, you've heard of fast twitch and slow twitch, or aerobic and anaerobic muscles, that here your type 2B muscle fibers decline pretty rapidly with age. So what does that mean to us? What we did is this kind of fun experiment where we took a little microphone called an accelerometer, and we put it on the soleus muscle of people of a range of different ages, and we asked them to stand perfectly still. And nobody really stands perfectly still. You sway, you go through postural sway, and as you lose that control, you can get out of this comfort range and fall over. So these postural muscles are really important to keep you upright. And what you see, and I'm going to see if I can I point? Is that what this is? I'm going to shut everything off. There we go. So what you see is not a graph as a function of time, but a graph as a function of frequency. It's called a fast Fourier transform. So you can see here going from 0 cycles per second up to 50 cycles per second, 50 hertz. And what that is showing you, particularly in the young person, the 27-year-old female, is that there is, I have no idea what this thing, where it's pointing. Can I do it here? It doesn't matter. Stick with me. That here, from 20 to 50 hertz, you could see a rise in information. That's called the spectral content of your muscle. Your muscles are really inefficient motors. We tend to think of them to use to pace back and forth on a stage if you're giving a talk. But in reality, your muscles are bombarding your skeleton with these higher frequency domain oscillations, vibrations. Your muscles are vibrating as they're contracting. And lo and behold, as you age, because of this muscle fiber type sarcopenia, that higher frequency domain, this 20 to 50 hertz realm, disappears. And we think that that is part of why Yannick Noah's arm is so big, or the absence of it in space, why bone is disappearing. We thought, well, what if we provide a surrogate for it? What if we put in those vibrations without necessarily having to play tennis? And this is the picture Yishen was talking about. This was in celebration of Stanley Kubrick's 2001: A Space Odyssey. National Geographic did sort of Where Are Humans in Space issue in 2001. Pretty obvious causal versus correlation. And this picture, they came take this picture of me and a turkey, not a chicken. It's really great. It's, it's like folds out, and it's a 2-page picture. And I'm thinking, wow, my ego is just exploding, thinking how great it is. My mother points out to me that the caption reads, Dr. Clinton Rubin, parentheses, right, and his subject, the turkey, left. Da, da, da. So it sort of puts us in some context. But really what you see here is the device we're going to use to put in these regulatory signals into the skeleton. And just very quickly to emphasize, again, going back to our postural sway and these loads causing deformations in bone, you could see this sway. We as humans sway about 1 cycle every 2 seconds, or a half a hertz, right? If you drink a lot of liquor at Thanksgiving, you're not going to sway more quickly, you're going to sway more, right? And that's when you fall over. But on top of that, those squiggles are actually what we're putting into the system. They're exceedingly small and barely detectable, very difficult to perceive. What we see very quickly, not to get into detail, but just to show you, as we increase the amplitude, we increase the volume of these vibrations, we stimulate more and more bone, which is kind of cool. We're turning on the formation of bone. And this is also fun because this is a paper we published now 24 years ago, where we got a bunch of volunteers in collaboration with Simon Turner, there in the middle, these sheep. And we set them up so that in one pen was, they're standing on a plate. You can see it here. Should have cleaned it up, right? Standing on a plate that's turned on, and the other ones are not turned on. So basically a double-blind, placebo-controlled trial. We got their consent to do this, and we did this across a year, 20 minutes per day for a year. And what this is a really high-resolution CT scan of the femoral condyle right here, about the size of a sugar cube. And you could see the animal's exposed to this small buzzing. The bones are stronger and denser. And we use this information to actually get into the clinic. But, first bit of data, this is a collaboration with Dr. Uzer at Boise State. He takes these mice as a function of age. So he now buzzes them for, 19 months. I mean, these are old mice now. And the interesting thing is that in looking at what they're doing on their wheel, on their running wheel, they aren't running longer. This is voluntary, you know, what else are you going to do in your mouse cage? You run on a wheel. They're not running longer, but they're running faster and covering more distance. So after this many, many months of very short durations of these, their musculoskeletal system is more interested in being higher quality. Ishan also mentioned some of the work that we're doing with cancer. This is in collaboration with Gabe Pagnotti and Teresa Guise. There's a paper that's coming out in Nature Communications, hopefully by the end of the year. But what this is doing first is looking at complete estrogen deprivation. So we ovaryectomize the mice, and we give them aromatase inhibitors, just like you would with a patient with breast cancer. Our physician colleague in here can explain this more specifically. But what this shows is if we buzz these mice, if we vibrate these mice, they have better grip strength, they're stronger, their muscle quality is much improved, and there is more bone. So more muscle, more bone, and even in the face of estrogen deprivation. But what does it mean to cancer? And you're going to see why I'm talking about cancer in a minute. But in essence, what we've got is we're now looking at the lesions, the breast cancer lesions which reside within the bone. And by buzzing them, vibrating them, and giving them a zolendronate, which is an anti-resorptive agent, can I go back? That what you've got is you've got fewer lesions that are pervading less of the bone. So we're thinking that maybe this is a way to get in to the clinic in treating bone. It turns out we're doing 2 breast cancer trials now, one at the University of Indiana and one at University of Buffalo, or Buffalo University, I can never remember which it is. But this is basically saying that buzzing is slowing down cancer lesions. So now we want to get into people, right? And I'm interested in outcomes in people. And the first thing we got to do in order to get past IRBs, the internal review boards that say that it's safe, is we have to demonstrate that the signals are not damaging. So we go off to Sweden in collaboration with Malcolm Pope, and we put pins into people's spines and pins into people's hips, and we oscillate them on the plate. And it's interesting because it shows with the solid line there is the acceleration and deceleration of the plate, sort of like being a very fast, short traveling elevator, up and down, up and down, up and down. And the dashed and dotted line is the transmission of the acceleration from the ground up to the hip and spine. About 80% of that signal actually gets through the articular cartilage. It's something called Biot's theory, which you don't really care about, and I don't either, but it does actually work. Another reason this is here is because of work that's in revision of PNAS right now, again in collaboration with Dr. Uzer. This is actually a cell, not a person. The blue is the nucleus, the green is the cell body. And we're oscillating the cell, and what you see is this phased motion between the two. The nucleus is moving differently than the membrane. So we think that it's through this actin skeleton, the thing that ties the two together, that's actually controlling the transcriptional machinery of the cell. And I'll actually end with talking very briefly about that. But more importantly, this blue line in the middle, that's what we're doing. You think about G force. 1G is what glues you to the ground. When we walk, we sort of walk at around 1.2 G with our heel impact spike. And we're here at around 0.4 G, or 40% of G. Very, very, very small. Now, you've probably seen on TikTok or in your, at a gym, these Home Depot paint shakers that people stand on, right? So these are exceedingly dangerous. I mean, can you talk percussive injuries to the brain? Go stand on one of these things. So while we're generating basically 0.4 G, these big devices in gyms are generating at 8 G at its lowest level. And that's transmitting right up into your head. Not to mention, we're talking about osteoporosis and people that are frail. It's probably about the last thing in the world you want to do. So be safe out there. All right, let's get to some clinical outcomes because this is really sort of what I like. One of the first studies we did, this is my old secretary. I convinced her to stand on a plate so I could take a picture. Promised I'd never show it to anybody. That in essence, we did a group of postmenopausal women, 3 to 8 years past the menopause. What we're able to see in the green being placebo, double-blind placebo-controlled trial, and blue being active, that we're able to slow the loss of bone over the course of a year, right? Without using drugs, which is pretty cool. Interestingly, we found that heavier women didn't really lose much bone as a function of time, but lighter women dumped it pretty quickly, but the signal saved and preserved the bone. We then moved, and it's sort of one of the great things about being in a university and having you all as colleagues, is that people will contact you about, well, you know, I got this problem. You know, what do you think of this? And what I didn't know is kids with cerebral palsy have really damaged skeletons, right? You don't tend to think of it that way, but they're not out playing soccer every day. And so your skeleton, because they're not Yannick Noah, can basically waste away very quickly. So we did a 6-month study on kids with CP. We used CT scans rather than DEXA to monitor their changes. And what we saw after 6 months is scary data. The placebo group is dumped 17%, or was, sorry, 11% of their bone, their trabecular bone, that structural bone. But the buzz kids gained 5%. So this sort of 17% swing just by standing on a vibrating plate for 10 minutes per day. In the frail elderly, this is done in collaboration with Doug Keel at Harvard and the Vibes group. We had people at average age of 82 studying on this, and 2 years later saw an improvement in the density of the femoral neck. Right? So these are things that ideally are going to preserve bone quality and resist fractures. Moving from bone to posture, remember I'm talking about the turkey at Thanksgiving, right? That this is a study funded by NASA. There's an old graduate student, Jesse Muir, that we had volunteering to lie down in bed for 90 days without getting up once. I mean, they were paid a lot of money, but you know, not for me. And what you see in this sort of blue squiggle on the top is how much they were wobbling before they laid down, right? They're standing, they're kind of stable. And here, after 90 days of bed rest, and once they get out of the sort of cone of stability, that red line, they have a tendency to fall over. And it's not good because you can break your femur, but imagine without gravity traveling for 9 months to Mars, and the first thing you do is fall over and break your femur, right? Not such a good idea. So what we saw with these buzzed people, we set up a harness system just like we designed for the International Space Station. And what we saw is that if you're buzzed, very briefly, that you could suppress the loss of instability, the loss of stability. Sorry, that's a triple negative. What does that mean to the clinic? So forgetting for a moment about 4 astronauts crazy enough to go to Mars, let's think about the aging community. This is a large group of people in a assisted living community in Hong Kong. We're looking at a 1-year and then a 2-year study, and I couldn't quite figure out how to put this up as an image that would be sort of gratifying to everyone. But if you just look at the number of falls, there were close to 50% fewer falls at 18 months in the group that's buzzed, right? And falls, just where I started, falls are bad. Falls are a bad indication of your musculoskeletal health. Leads to fractures. We didn't have long enough or enough people to show a statistically significant change in fractures, but it was heading in the right direction. So those that fell were at risk of fracture. Those that fell in the vibration group had fewer fractures. This is also showing that a year after they stopped using the device, legs were still stronger. And then finally, again, learning from my colleagues, this is in collaboration with Carrie Winter-Stone at Oregon Health Sciences University. Maybe you knew this, I did not, but if you go through chemotherapy, 90% of people that go through chemotherapy, 90% have complications of peripheral neuropathy. And at 6 months, still 50% of people are having neuropathy, are still suffering from consequences of neuropathy, right? So this is modern medicine causing a pretty devastating condition. So we took these people 6 months out, and this is called a Cohen statistical test. Don't ask me what it means. It's a quick and dirty way to look at clinical significance. And there are no FDA-approved ways. It's just called usual care, hope for the best, right? That the blue bars, and maybe you could see, are basically saying in each one of these cases that by being buzzed, you have greater function, greater muscle strength, your ability to get out of a chair, right? Your speed, timed up and go, are all benefiting from this, right? So this is pretty exciting stuff, at least for me. And we're chasing this now with a major multi-center grant, also very fun. But let's head down kind of the home stretch here. It's just not old people that get osteoporosis and risk of fracture. Young women, a lot of anorexic women, really have crappy bone density. We deal a lot with women with anorexia. These are recruited young women between 16 and 20 years of age, right? If you're 20 years of age, you don't want to take a bone drug for the next 7 decades, right? Who does? So we have these devices that they stand on, and we're able to show with something called intention to treat. This is including everybody in each group, that we're seeing significant benefits to the cancellous bone density in the spine. We're seeing significant benefits of bone density in the femur, cortical bone density in the femur. And because we use CT scans, we saw increase in paraspinous musculature. So we're beginning to connect all these tissue systems together. If you look at them in what's called a per protocol analysis, we're looking at those young ladies who use the device for 2 minutes to 10 minutes per day versus those 2 minutes and less and the controls. What you can see is quite a marked suppression of fat, right? Because if you're forming muscle and you're forming bone, those cells have to come from somewhere, the mesenchymal stem cells. We are stimulating, driving them, we're forcing a lineage selection into these higher end musculoskeletal tissues. They're making a decision and they're not becoming fat, right? So these women actually have less fat a year later. So to try to really look at this, we looked at mice both in a low-fat and a high-fat diet, and we buzzed them for a number of weeks. And then we did CT scans, in vivo CT scans, where now what we've done is we've erased the guts and erased the muscle, and all you see is fat. So gray is fat, both subcutaneous and within your vital organs. And what you see is almost 30% less fat in these mice eating exactly the same amount each day. And so while I was very proud of being published in one of the great scientific journals, National Geographic, this led to a huge amount of press, which was really cool, front page of the New York Times, a whole bit. Who cares? I don't care. It made it to a comic strip. And if you can't read it, or maybe you can, maybe you can't, but the amazing thing here is basically 20 years of my life reduced to 2 panels of a cartoon, and she captured it perfectly. I have this framed in my office with all the editorial comments on it, et cetera. It really was cool. Back to cancer, and then on to other systems. So in collaboration with St. Jude's Children's Hospital, we looked first at kids in cancer remission. Kids that have actually gone through cancer treatment, A, have crappy bone, and B, have increased adiposity or more fat. So we buzzed them, and what we saw, intention to treat and per protocol, we saw marked statistically significant increases in bone quality. What's not in this paper, and which I finally extracted out, is there's also less body fat in the buzzed kids, which is actually a real problem with everyone going through cancer treatment, is the increase in adipose tissue. This is really exciting because St. Jude's has now allowed us to go into a pediatric population suffering from active cancer. So that's a study that's ongoing right now. All right. Now I'm going to really quickly, and I'm going to do this quickly because I have very little data and less confidence in it for sure. But this is in collaboration actually with my sister at UNC. And what you got here is looking at all these pretty colors are showing how a cell is put together. And you can see 3 hours after buzzing these cells, they have a more robust cytoskeleton, right? They're bigger, stronger, meaner, right? Your cells, just like Djokovic, not Djokovic. Where did I start with the tennis player? It wasn't Venus Williams. Doesn't matter. Yannick Noah, showing my age here. Holy moly. That what we've got, but the interesting problem with this is 24 hours later, Djokovic, 24 hours later, the cell is back to being a couch potato. That's why, if you only go to the gym once per week, Carl, it's not good enough. You gotta go every day. But you don't have to do a lot. You just have to stimulate your cells. You have to get out of that couch and actually do something. These adaptations are transient. Okay. Last 2 slides, promise. And this is a collaboration with Etty and Chris here in the front row, or second row. This is now looking at the immune system. And these are now T cells in an incubator, no longer in a person. Actually, I believe they're from Chris. There's a dedicated graduate student for you, pulling out his own T cells, and that we're vibrating them in an incubator, right, is a way to enhance, like in CAR T therapy, where your T cells get engineered to fight cancer, but can you expand them or stimulate them proliferate quickly enough to be of use to the patient? It's a real problem. What we see at the top scale there is an increase of close to 50% over 5 days of the number of T cells that are buzzed. But to us, particularly we old folks here, this is the number of T cells in us, right? So this is a group of cell populations from an old group of, I think it's 12 per group, and old that were buzzed, young under 30, old over 65, sorry. That in essence, you could see a bunch of things here. One, there are a lot fewer T cells in old people. Susceptibility to disease, right? It's where I started. By buzzing them, in the young people, it's about a 13% improvement. Okay, not bad, I'll take it. I mean, COVID's dangerous, right? Or is it? I forget. The old data is showing a 50% increase in number, right? We go through, and Chris has been very great at sort of going through the hardcore biology of it. This is done also with Brian Sheridan in molecular genetics. Very grateful for his contributions. But basically, it's showing that these T cells, not only there are more of them, but they fight disease better. I don't have time to go into that yet. But then finally, and hopefully Elizabeth Bick is not in the audience. Those of you in the biomedical world know who that is. But this is a collaboration I'm doing with amazing colleagues in pharmacology and also molecular genetics. And it's really kind of fun. Because remember, I started, oh so long ago, talking about cognition and risk of decline. And we've talked about all these progenitor cells being sensitive to mechanical signals. And that exercise is good to slow down Alzheimer's and cognitive dysfunction. So why not brain cells? Why not? So here what we've got are oligodendrocyte precursors that are being exposed to vibration. This is in cell culture. And we're seeing a marked increase, I think 250% here in terms of differentiation, this marker showing that these are becoming more mature oligodendrocytes, and here, more of them. So more reasons to exercise. Don't believe a word I say, just go out and exercise. But here, my last slide, is work that's actually from the brain of a buzzed mouse, or actually two brains. On the top is a control mouse, and the bottom is a buzz mouse. This is complete poetic license. We have very little data to support this. Never stopped me, so I'm going to keep going. That there is less inflammation in the brain. That's what this is stained for. And just in closing, see if this actually works, another picture. You may be the only person in this audience who knows what this is. No? This is the Veil Nebula, which looks just like an inflamed brain, if you ask me. So with that, I would like to thank you all for your patience. I'd like to thank everybody in our lab. Not everybody in our lab gets married, but here's Etty getting married, and here's a number of people in our lab group. And just to tie it back to oscillating neutrinos, Albert Einstein said everything in life is vibration. Thank you very much.
Any questions?
It seems to me that the frequency range that you use on these plates, how does that connect to sport and activity?
So again, going back to the muscle being an inefficient motor. So the way your muscle contracts is not just to pull it and hope that you can lift up your beer can, but rather the way that it works is through the spectral content of muscle contractability. So what we did is we thought, well, why not just actually bathe the signal with a 20 to 50 hertz, representing this higher frequency domain. But the FDA told us we had to select one. So we went dead center and went to 30 hertz. It turns out that it was kind of lucky for us, because remember I talked about BO theory and transmissibility, that it turns out that above 30 hertz, by 35 hertz, 40 hertz, 50 hertz, the transmissibility function fades to gray. It doesn't exist. So the way you can get these vibrations up your axial skeleton is to choose the frequency very, very carefully. The other thing is that, let's just say you don't believe this and you think that it's 1 hertz or 2 hertz, 2 cycles per second is good. You still got to put in thousands of cycles, right? I'm standing here, right? You could say that I'm in a static condition, but right now I'm in a very dynamic environment. My muscles are just, swamping my skeleton with these high-frequency domain signals, right? Thanks, Axel.
So I have a question here.
Hi.
Great talk.
Oh, thank you.
Really enjoyable. So I was wondering, if you're looking at, or if you have ideas about the cellular mechanism by
sure.
which this is happening?
Do we have to be out of here by 9? Right. So I didn't get into that because usually, particularly following such a great talk, if I was stuck talking about signal transduction mechanisms, I'd be snoring. So it is something we study, and with colleagues really around the country, around the world, looking at sort of mechanobiology. How does a cell perceive and respond to a mechanical signal? I thought this would be fun because it talks about outcomes, right? Am I going to be healthier if I go out and exercise? But the actual molecular mechanisms, both in terms of the biochemical transduction, right? We are great believers in the Wnt beta-catenin pathway, which is evolutionarily conserved. It's all in all cells, right? I mean, remember, life hasn't been around relative to the Big Bang Theory. It's only been around for 2.5 billion years, give or take. It's not that long to evolve a number of different distinct systems. So there's this ubiquitous conserved element of the biochemical pathway. On the physical side, then we talked about the actin skeleton, right? We all know about focal adhesion kinases, which connect cells to substrates. But it turns out that when in blood, that doesn't really count because your cells are floating around, not attached to anything, that in essence, there's a nuclear structure called the link complex, which is the connection between the membrane through the actin skeleton to the nuclear membrane that transmits across the membrane through something called link. So we do things like, we study link. This is mainly my colleague Ganesh Uzar out in Iowa. But what we do is we go and we downregulate it, and we show that your cells are no longer responsive. So there's less link as we age, and it's less functional as we age. So maybe someone like Gabor can go and CRISPR in link into our cells, and we'll all end up being thick-headed.
Can I make the last question? As a fellow speaker.
The speaker's prerogative, huh?
Yes.
Strawberry ice cream, thank you very much.
I got a text message today, some guy, something like my colleagues, over 60 or something, he said he ran a half marathon and is very proud of it. I have a theory that too much exercise is not good. And so I would like to see if you put this vibration or whatever too much, what happens? Have you done this study?
It's a great question. And it goes back to this issue of exercise is good for you, but like all things or most things, except for red wine, too much of it can be bad for you. And that's exactly the experiments that we've done. We find a stimulus that turns on cells, whether it's through the link complex or whether it's people standing on a plate. And once we find the cells respond, giving them more you can't push your gas pedal to the floor any further. You've stimulated proliferation, you've biased differentiation. You can't do it anymore. It's set in stone, so to speak. So yeah, marathon colleagues, they're brave and it gets their endorphin levels up. There are lots of benefits to it. But in the end, most things in our system, evolution wasn't there to go. Oh, somebody's telling me to shut up, probably. So evolution doesn't really prefer zebras that can run for thousands of miles away from cheetahs. They just want to get away quickly, right? And imagine if your skeleton is crappy and a cheetah is following you, you step in a pothole, you break your bone, that's trouble. So you want a system, an evolutionary tuned system that is quick to respond, but who wants to go out and run a marathon every day? Not me, not you. I can see that, right?
Two questions. One is, when is this device going to be commercially available on Amazon? Okay.
Let me give you my card.
And the second one is, being little on in age, I go on YouTube and I see hundreds of videos on do this exercise, do that exercise for.
You need to change your YouTube channels, I think, is what you need to do.
Okay, got it.
Right. So as I started off with my disclosures, conflict of interest, rose-colored glasses on, yes, and thanks to intellectual property partners and the lovely primordial soup of Stony Brook, they encourage seeing your research actually translate to the clinic. And I will point out, as I've pointed out to many medical school deans in the past, not this one yet, but I'll get to them, that this cliche of bench to bedside only works if you involve the commercial sector. If all you're interested in is covers of science, who isn't, it's never actually going to improve health and society. You need to involve industry in this. I have it tattooed on my shoulder blades. I'll show you that later. But so yeah, we actually manufacture this device and versions thereof. It's made by a manufacturer in Germany who licenses the work from Stony Brook. They have a global distributor, and it's kind of fun until you actually, rather than going to YouTube, you go onto TikTok, and you can get on a vibration TikTok channel. Why you would do that, I don't know, but people in leotards, men and women, standing on vibrating plates, quoting me about why they should buy a vibrating plate from them. So it's kind of, I spent 40 years trying to get people to listen to me, and it's a captive audience. I finally have you. But yet TikTok does it overnight. So it's a problem just because too big a signal is dangerous, right? It's look at NIOSH or Occupational Health and Safety, International Standards Organization, these societies to try to protect us from these pathogens in the workplace, including vibration. Helicopter pilots, truck drivers, people who use handheld machinery, getting Raynaud's phenomenon, hearing loss, back pain. It goes right back to the question of too much of a good thing. So that there is, I think, as Axel puts it, a sweet spot where we can work.
Thank you very much.
Thank
Let's
you.
give one round of applause.